Alright, here's a follow-on video to page tables and translation look-aside buffers. So first I slaughtered it when I explained it to you guys in class. That's my fault, and I want to fix it. Two, the text doesn't really give us sufficient information, so I've updated the skills to only require you to know this information for exam purposes at this point. And I'm going to talk about it. And then for those who are super interested, I'll tell you when. The second half of this short, we'll be talking about another course text explaining in more detail how it works. So where's the page? Where and what is the page table? So the page table, right, is just a translation between physical addresses out on disk and virtual addresses, disk or RAM, and virtual addresses that the processor thinks exist in RAM. Like we talked about in class, this exists for two reasons. One, to make the processor think we have 4 gigabytes of RAM, for example, when maybe we only have 1. And two, because of the most recently used principle. So we're kind of betting on most recently used, so we don't call it on our bluff, but every now and then we do. Really simple. All that happens is, I'm going to go to the solutions here, is we're given a virtual page number and page offset by the processor, and then the CPU, and then the translation page table that's stored in RAM for each process will determine what the physical page number is and the page offset. So physical page number, if it exists in RAM, and the page offset for where within that specific page that exists. Remember, unlike cache, right, in RAM, physical memory, we talk about pages, and so we call them pages, and so physical memory is divided into pages. In this case, this example shows 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe 8 or 10, I don't know. Anyways, a number of pages, right? And the most common accepted size is 4 KB. And so these pages, right, are referenced and where within that page based on the virtual address that's given. Okay, so what you need to know, right, is the virtual address that's given is going to have some virtual page number, because if we say there's 4 gigs of RAM and divide by 4K, you're going to have some thousands numbers of pages, whereas in reality, if we only have like 512 K RAM, or 512 megabytes, excuse me, of RAM, and we divide that by 4 K for our page size, right, we're going to maybe have 100 pages or 128, whatever it is, pages, so it'll be a limited number of pages. So that's where we get this translation between the virtual and physical. That presumes that it actually does exist and it is in main memory, okay? So generally it's going to have a valid bit, meaning it's actually used, it's actually assigned, allocated. And then really what a page table usually has is valid for if it's assigned, dirty, meaning it's been written to in RAM, so it needs to be written back out into disk storage. And reference helps the RAM and CPU decide if this physical page is used often or not, so it can either discard it or keep it. Okay. All right, so that's the page table. The page table, as it says here, each program has its own page table stored in RAM with a pointer register referencing it. This is somewhat a simplified explanation. It depends on the implementation of the system, but good enough for the class. Okay. And in this case, one of the interesting things about this is that since each program has its own page table, whenever we need to go look in RAM to translate a virtual page to a physical page, that's one time cost. And then once we find it, we actually have to load that from RAM into cache. So again, this is the intermediary, right? Main memory, RAM, in between cache and disk. Okay, so that's where this page table is existing in RAM. So when we look for these pages, we have 2 prices to pay. 1, finding the page table. 2, if the page is there and can be translated to physical, then loading that physical page. So what they did is created what's called a translation look-aside buffer, and it's actually cache that's located in main memory, and it's just a small list, and it's really based on the principle of recency, meaning that whatever's accessed will likely be accessed again in the near future. And so it has a valid dirty reference, a tag, and a physical page address. So it's like a shortcut to basically find if a physical page is loaded in, if a virtual page, which is here, is located. So it's going to have your virtual page here and your physical page. So it's a translation. So it's an immediate translation. Virtual page right here, physical right here. And it'll look. Now, just because it doesn't exist in the TLB doesn't mean that the page table isn't out there. So the idea is first we search in the TLB. If it's there and we find the address, great. If it's there or missed, then we've got to look out in the page table. And then finally, if that's a miss, then we've got to go all the way out into disk and pull it in. Okay, so that's sufficient for this class. So from disk to main memory and then all the way down into cache. That's sufficient for this class. Okay, the book gives a good picture showing this kind of all coming together, going between, here we go. There we go. Going between virtual to RAM all the way down to cache. Okay, so that's it for the class. Now, the book doesn't do a good job talking about how do we do all these addresses, and Dr. Glock had a nice skill set on all these, but it requires additional teaching that's missing. So this from here, what follows here afterward is if you're interested, all right? So a good book that talks more in detail about this is Modern Operating Systems, and it talks about paging and how it works. And I like the example they give because, as you can see here, it gives it in ones and zeros. The skills are all in hex, which leaves a little bit of confusion, and this is where I butchered in class translating and all of this. But basically, right, we have our virtual address right here, and the translation that occurs in the page table to the physical address. So in the example they give, which I like, the virtual address that comes in, it has an offset, right, of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits, okay? And this is the address that that points to, okay? And it has a page portion of 3 bits. So this is 15 bits altogether. So the 3 bits here allow us to, this is what I was trying to explain in class, right, to the third there. So they allow us to reference 16 pages, okay? And then the offset right here, right, is what we use directly to translate to physical. So if this is the virtual address delivered, we take that, we find the virtual page number in the page table, which it points here to, and that will tell us if the physical, so again, here's the present absent, if it's actually there or not. This is different than the book we looked at for class. This portion was on the left side over here, but anyways, it's on the right side here. So we go to virtual page 2, and it translates it to the physical page here, right, of what, 2, 4, I think it's 6. It translates that. So then to translate and get the final physical page number, we take that value, translate it to the physical page number, and then we just carry the offset width completely, and the final outgoing physical address is this. So it gets us to the correct page and then gets us to the correct offset within that page. And then what happens is all of this is loaded onto the buffer. So the CPU is clueless. It just theoretically, depending on the system, but as an example, it just delivers this address to RAM. RAM translates it, grabs this, and then puts what's at that memory address onto the buffer, the memory buffer, to be delivered to the CPU down to cache, and it's transparent to the CPU. So CPU has no idea that what it's sending here is not actually a real address, but the page table translates it in RAM, and then it delivers the memory there. Okay. Now the translation look-aside buffer, right? is cache located in RAM, and it can all be searched simultaneously. It's hardware and a bunch of gates put together that, like we saw earlier in class, I think there was Appendix B and Chapter 4. All of them can be searched simultaneously, and so one hit to the TLB delivers the answer if it's there or not. And so the TLB looks more like this, right? So this is a more realistic example, and it's an immediate translation. And so first has a valid bit, okay, and then this is what in our other textbook we called dirty bit, right, if it was written to or not. And then this shows realistically in more modern systems the type of read-write ability we have with that memory. Our text doesn't talk about this. But it's immediate translation. So we kind of forego, if it's a hit, the page table. So the CPU passes to the TLB, for example, virtual page, let's do 140, right? And it says it's a hit, it's located at physical page 31. So it just immediately sends it to the page frame, the physical page frame 31, right, with whatever other addressing it needs. And so this is much faster, fractions of the amount of time it takes to search the TLB for each page that has a TLB and all the information in it. So that's a more detailed explanation. Again, about halfway through this video I said, hey, here's all you need to know for the class. If you want more information, there's plenty of other information out there.